Hello everyone, I'm Karen from MDPI and I will be your host for today. Thank you for joining our latest MDPI webinar on nanomaterials, entitled Advanced Mechanical Modeling of Nanomaterials and Nanostructures 2. This is the second webinar on nanomaterials based on special issues from our journal of the same name. If you're interested in submitting your paper to the special issues that are linked to this webinar, please check the webinar's webpage. I would like to remind everyone this webinar is recorded. The recording will be made available as soon as possible. It will be posted on the webinar's webpage. The webinar is also being live streamed on MDPI's YouTube channel, and hello to those of you watching us on there. Furthermore, I would like to say that certificates of attendance are available upon request to nanomaterials.webinar@mdpi.com. We can only prepare certificates for those of you registered and watching on Zoom, not on YouTube. Today's webinar is chaired by Dr. Francesco Tornabene from the Technical University Sofia in Bulgaria. Thank you, Francesco, for accepting to chair this webinar. There will be two presentations today, given by Professor Dr. Carola Esposito Corgione from University of Salento, Italy, and Professor Dr. Victor R. Eremejew from Gdansk University of Technology, Poland. The talks will be followed by a Q&A and discussion moderated by the chair. If you have any questions, please feel free to post them in the Q&A box at the bottom of your screen. Please make sure to mention the speaker to whom you're asking the question. And now it's time that I hand over the floor to Francesco. Enjoy.
Thank you very much for this presentation. I start to share my screen because I have a little presentation regarding this second webinar. Okay, I think that you can see. So is the second appointment regarding advanced mechanical modeling of nanomaterial and nanostructures. And this webinar is related to this special issue that is organized by me and Professor Sana Dimitri. I want to say to all the attendees that if we want to contribute with a manuscript or submission, the special issue is always open within the 23 April 2021. So here I report some of the papers that we have already published in this special issue, and others are under review, and some other colleagues have promised that we will submit to this special issue. So regarding this webinar, I want to highlight the topic. And so, in line with the interest of the special issue, Advanced Mechanical Modeling of Nanomaterial and Nanostructures, the present webinar will focus on the theoretical and numerical modeling of a heterogeneous material and enhanced structures whose response could be affected by stacking sequences, play orientation, agglomeration of nanoparticle, volume fractions of the constituent, and porosity level. The series of talks will show different results for large numerical campaign focused on fiber reinforced composite and laminates, functional grading materials, carbon nanotubes, graphene nanoplates, less auxetic material, lattice and cell honeycomb materials, Mars constituent, together with innovative and advanced classes of composites such as variable angle tow laminates. Among many possible structural applications, composite beam and shell with different geometry will be discussed due to their unique shapes and outstanding mechanical behavior, accounting for their possible size dependence. In a context where an increasing computational demand is required to solve such complicated solid mechanical problems, the webinar discusses about different high-performance computational strategies and advanced theoretical formulation, which are evaluated systematically against the available literature in their reliability and accuracy. So, I show you in this slide the program. We will start with the first talk by Professor Carola Esposito Corcione, and the second talk is by Professor Victor Emery. So I will present the first speakers, and the Professor Carola Esposito Corcione. She received her PhD degree in Material Science Technology in 2004 from University of Salento. Her research interest focuses on the rheological, thermal, and transport property of innovative polymeric materials, and in particular of polymeric-based nanocomposite biopolymers, large employed in industrial application. Focusing on the relationship between processing, structure, and property. She is author of about 120 papers on international journal and 70 presentations of international conference and 4 patents. So the talk is entitled Cure Reaction of Epoxy Resins Catalyzed by Graphite-Based Nanofiller. So Professor Corcione, please share your screen and you can start with your presentation. Thank you very much. Enjoy.
Thank you, Francesco, and good morning to everyone. I will present a joint work between the University of Salento and the University of Salerno and the University of Leuven. And at first, I would like to spend few words to describe Salento and in particularly its university. So, the University of Salento is located in Lecce, that is the main town in Salento, in the southeastern of Italy. And I am a part of a research group that is focused on the rheological, thermal, and transfer properties of innovative materials. And in particular, our research is involved in the study of polymer-based nanocomposites, for example, biopolymers and also nanocomposites with commercial polymers. And we are also interested in a lot of industrial applications. In particular, at the University of Salento, our research group have a lot of laboratories that are involved in different kinds of study of materials, such as, for example, structure and thermal properties of materials, but also rheological and durability studies and mechanical characterization. And also we have a very long expertise in 3D printing. So the first part of the work that I'm presenting today concerns the possibility to add graphitic-based fillers to thermosetting polymers, and in particular to epoxy resins. It is well known, in fact, in literature that graphitic materials could have a dual role in thermosetting materials, not only as fillers to increase all the mechanical properties or thermal properties, or also electrical or barrier properties of the materials that are very important in a lot of fields of the industrial applications, such as, for example, in automotive or for example, mechanical applications. But we are particularly interested also in another possibility, that is the possibility to add graphitic-based fillers, nanofillers, if possible, to thermosetting polymers to increase the curing reaction of the polymers. So we would like to analyze the possibility to use these nanofillers as catalysts for many curing reaction of thermosetting polymers. So we know that this is possible because in our previous work, we noticed a significant activity of these fillers in increasing the curing reaction of thermosetting resins. In particular, in previous works, a significant effort was directed by University of Salento team to the preparation of epoxy nanocomposites reinforced with nanographite and to the analysis of their structure, rheological, mechanical, and thermal behavior. Moreover, other additional studies performed by University of Salerno in Campania, so University of Salerno team, have shown some catalytical activity of graphene oxide layers on the curing reactions of different epoxy resins. In details, direct kinetic studies with full chemical characterization and quantity evaluation of the low molecular mass products for the reaction of a typical commercial epoxy resin with monoamines as well as with alcohols were conducted at the University of Salerno. In this work, so in the work that I want to present today, the influence of different graphite-based nanofillers on the same epoxy resin, so on the epoxide ring opening reaction as induced by amine for a typical epoxy resin that is named DGABA, so diglycidyl ether of bisphenol A, studied by indirect techniques such as, for example, calorimetry or rheometry is presented. So I also want to indicate that the results obtained with the joint work between the University of Salerno and the University of Salento show a relevant activity of graphene oxide on the epoxy resin cross-linking. So in that occasion, we attributed this behavior to the ability of graphene oxide to catalyze not only primary amine epoxy and secondary amine epoxy addition, but also hydroxyl epoxy additions, so esterification reactions. So now let me start to the work that I want to present today. So you can see in these slides the material that we used for this experimental work. So this ether of bisphenol A and isophorone supplied by Aldrich and used as any further purification, as you can see in this slide. And also we used expandable graphite flakes intercalated with a mixture of sulfuric acid and nitric acid that were obtained from anthracite industries. The commercial name of this graphite was EG3772. And after a rapid heating at 700 degrees, so about 2 minutes at that temperature, expandable graphite flakes were expanded and then further disaggregated by sonication in a solvent, leading to expanded and sonicated graphene stacks that we named in our work EGOS. So on the other hand, graphite oxide named GO samples were prepared by Amherst oxidation method at the University of Salerno from Professor Guerra team, starting from synthetic graphite with a high surface area named HSAG. So, as you can see in my slide, we can understand that exfoliated oxide, also named GO, but with E before, so EGO samples were prepared also by University of Salerno. So Professor Guerra team, starting from GO powders, introduced in a ceramic jars together with stainless steel bowls and dry milled in a planetary ball mill for 2 hours. So let me know now what is the study that we performed together with the University of Salerno. In this slide, the indirect results obtained from DSC and then from rheological measurement related only to the introduction of EGO, so of the last filler that I talked a few minutes ago, inside the epoxy resin are discussed. So you can see the effect of the introduction of EGO filler compared to the thermal behavior of the epoxy resin, of the net epoxy resin in absence of the filler. So the overall direct kinetic studies that are referred to the use of all the other fillers that I talked before are also contained in a joint paper that was already published between University of Salento and University of Salerno. Here I would like to concentrate only on the effect of EGO. So as you can see in this slide, isothermal DSC scan at 50 degrees Celsius for the considered epoxy net resin without fillers and with 3% by way of EGO nanofillers are reported in this figure. And so, as you can see in isothermal DSC scans, a short interval time of about 30 seconds is needed between the heating ramp at 40 degrees minus and the isothermal test temperature to obtain a stable heat flow. So for this reason, all isothermal curves were corrected, determining by linear extrapolation the value of the heat flow at time 0. So ignoring the data collected in the first 30 seconds, the values of the isothermal Evol reaction and of the time to reach the peak are reported in the table inside the figure. So now I want to show you how we decided to model the experimental data that we obtained during our experimentation. In particular, the data shown in the figure indicates that the considered graphite-based nanofiller strongly increases the heat of reaction of the net epoxy resin. In fact, the heat of reaction that you can see in the table for the resin is 158 joule per grams. Instead, you can notice that it increases up to 337 joule per grams when you add just 3% by weight of the nanofillers EGO. Furthermore, the data show in the same figure also indicates that the time to reach the peak that I call the T peak measured in seconds is significantly reduced in presence of the filler. So as you can see, we can have a reduction of about 40% as was also expected, accounting for its catalytical activity in epoxy ring opening reactions. So in order to get further insight into the reaction mechanism, the rate of reaction d alpha and dt was also calculated from the experimental data reported in this thermogram. and was also calculated by using the equation that you can see in the slide, where BL is the baseline set as an horizontal line interpolating the asymptotic value of the heat flow at the end of the reaction, and dH in dt is the heat flow for unit mass shown in the figure, and HT is the heat of reaction obtained by integration of the peak of in figure for the net epoxy resin, and both also for the filled epoxy resin. Finally, alpha represent the degree of reaction. So as you can notice, the knowledge of the curing reaction can be used to gain a deeper insight into the possible catalytical activity of our nanofiller. So the isothermal rate of reaction can be interpolated with a phenomenological model that can help us to predict the kinetic mechanism of this epoxy resin. In particular, the isothermal rate of reaction of our systems were predicted by applying a very well-known autocatalytical phenomenological kinetic model proposed by Diane and Ruth Data, as you can see in my slide. So as you can see, we have in the figures reported in these slides, we obtained a very good correspondence between the experimental data and theoretical curve that we obtained by applying the model that you can see. In the model, we need to specify that M and N are fitting parameters, not depending from the temperature. Instead, K1 and K2 are temperature-dependent rate constants. And so the comparison between the autocatalytical model predictions, so the black curve, and the experimental data that for the epoxy resin are represented by a green color, and instead in that case in the presence of 3% by way of EGO, we have a red curve. So as you can see, the comparison between the autocatalytical model prediction and the experimental data of the epoxy resin, and also of the epoxy resin filled with the EGO, shows a good agreement between the experimental data and the theoretical model. Furthermore, the parameter M dominating the autocatalytical effect of at a low degree of reaction, and as you can see by the tables reported inside the figures, the M parameter is very close in both cases. On the other hand, the shape of the rate of reaction after the peaks shows some difference that are indicated by different values of N that is higher in presence of EGO. Another information that I want to stress is that the kinetic constant K1 and K2 are both higher when a graphite-based nanofillers are used in comparison with net resin. And this confirms the catalytical effect of these fillers. In particular, the constant K1 represents the initial rate of reaction. So the initial rate of reaction when the time is equal to 0. K1 so can be obtained from the experimental DSC data, and it is a very, very low value that increases when GO is added. On the other hand, you can see that the parameter M in this equation is representative of the increase of the rate of reaction at the beginning of the reaction, so low values of alpha before the peak. On the other hand, the parameter N in the same equation is dominant on the final part of the reaction, so in this case, high values of alpha. And the autocatalytical effect, as measured by the parameter M, is not significantly modified by by any nanofiller, while the parameter N increases, changing from values lower than 1 to values values higher than 1, sorry, when GO and also EGO, as you can see in this slide, are added to the resin. So a possible important explanation to this kinetic change can be addressed also looking at the differences in the peak time and in the heat of reaction. So as you can see in this slide, when the rate of reaction is very fast, vitrification responsible of reaction and this temperature is delayed as a consequence of non-equilibrium conditions corresponding to a difference between the actual and equilibrium free volume as occurs in cross-linked systems undergoing to fast reactions. At enough high rate of reaction, the actual specific volume is not capable to follow the equilibrium specific volume corresponding to the instantaneous molecular configuration, which depends on the amount of reacted groups. So this effect explains why in a faster reaction, a higher heat of reaction, it has a larger amount of reactive group is observed as a consequence of a delay in the vitrification. And so it is a very important result that we wanted to study not only by DSC but also by rheological studies. In fact, another important consideration is that at a higher rate of reaction, the specific volume is farther from its equilibrium value. And close to the end of reaction, this corresponds to a more rapid decrease of the rate of reaction and is a consequence of the vitrification of driving reaction ends. So the rate of reaction decreases faster when N is higher. And this is also evident from the last portion of the rate of reaction curves that are shown in this slide. So I think that this observation need to be confirmed by another techniques. So for this reason, we decided to perform a kinetic characterization of these both two systems also by rheological analysis. So for this reason, the rheological properties of the filled and unfilled mixtures, the same filled and unfilled mixtures, were also evaluated by monitoring the evolution of the storage modulus G the first and the loss modulus G second as a function of time, as you can see in this slide. So the measurements were performed by using a strain controller rheometer with parallel plate geometry, and the temperature of the measurement was 50 Celsius degree in order to compare to the results obtained by the DSC analysis. So the dynamic mechanical properties of occurring systems, as you know, depends on the degree of reaction and the dramatical change when the gel point is approached. So it's very important for us to understand where is the gel point of our systems. So the time to reach the gelation or the gel time, TG, that can be determined according to different criteria. So it's not very easy to establish what is the most correct criterion to determine the gel time. For example, the criterion of maximum peak in tangent delta, based on the point where there is a maximum difference between the elastic and the viscous behavior of the system, is very well known. But the criterion corresponding, for example, also to the crossover between the two modulus, so G the first and G second, is also well known, and at this point the system presents not only a viscous behavior but also an elastic response, says storing the same amount of energy than that was dissipated. So a long discussion between all the authors of this work was done in order to establish what is the best criterion to be used in this case. So criterion of the tangent line to the G-first curve. In this case, I want to say that this point corresponds to crossing between the baseline, so G second equal to 0, and the tangent drawn at G first curve when G the first reaches a value close to 1000 Pascal per second. So this value is very used in literature. So another one is the criterion of the viscosity. At this point, the real dynamic viscosity at a star reaches several determinant values. For example, 1000, 2000, or 5000 Pascal per second. In particular, there is also a standard ASTM that suggests to assume the gel time as the time needed to reach 100 Pascal per second. So you can understand that it's not very easy to establish what is the best criterion to use. So the gel time calculated according to the above mentioned criterion, so has the values that you can reach when the viscosity at a star at a 0 star is equal to 1000 Pascal per second is reported in our tables. And at the same time is these values, you can see the comparison between the results that we obtained for the net epoxy resin with the epoxy resin filled with 3% by weight of the same nanofiller that we are talking about, so EGO. And so now as you can see, you can notice that in our case, different initial viscosity were measured for unfilled and filled resin by changing a factor of about 2.5. So it's a very important difference. So this viscosity were always lower than 1 Pascal per second. So comparing the criterion proposed by LASA with the criterion proposed by the ASTM standard, it is important to notice that we decided to assume for us the gel time at those corresponding, as you can see in the table, to 100 Pascal per second. And so Finally, I also want to underline that the gel time is considered for a constant value of the degree of the reaction according to Flory theory. So it represents a fast way to compare the rate of reaction of thermosetting resins with the same reagents and under different conditions, such as a temperature or catalyst. So as you can see, we obtained also in this case, also with a different technique, a very important result and a similar trend that we also obtained by DSC. And I also want to underline that a similar trend would also be obtained adapting the different criteria that I illustrated before. So this result can be again rationalized by the strong effect, the strong catalytic effect of nanofillers based on graphite oxide on the epoxy ring opening reaction. So also in this case, we wanted to apply a theoretical model to predict the kinetic behavior of our analyzed systems. So the experimental gel time curves were fitted by using a Makosco model, where you know that alpha G is the degree of cure at which gelation point occurs, and A and B are fitting parameters. So we calculated alpha G starting from the XC experimental curves that I illustrated before by using the gel time measured from the rheological curves. So the theoretical prediction that you can see in this slide for both the systems, so for the net epoxy resin and the filled epoxy resin, are in a very good agreement. So the experimental results with the theoretical prediction, and also the fitting parameters obtained by fitting the experimental curves of these figures are also reported in the table, where you can compare the data obtained from the EpoxyNet system with that obtained for the system filled with EGO. So in conclusion of this first part, I want to point the attention to the fact that the influence of graphene oxide on the epoxy ring opening reaction of a commercial epoxy resin was studied by differential scanning calorimetry and rheometry, and both studies confirm a catalytical effect of the graphite filler, nanofiller on the epoxy ring opening reaction. So these results indicate a dual rule of EGO in the composite, so in the nano composite, not only as a loading fillers that can act on the mechanical properties of the final system, but also as catalyst for the reaction. So it has the possibility to reduce the curing the time, so the cross-linking curing time, and to increase in that way also the final properties of the systems. So let me now very quickly to the second part of this work. I just want to do something about this joint project, because the second part of the work is a project in collaboration with an Italian company, Costruzioni Motori Diesel CMD, which developed a plant for the combined production of electricity and heat by thermochemical decomposition or molecular dissociation of wood biomass at high temperature in complete absence or minimum quantities of oxygen. So it is a pyrogasification plant. In the table, you can see all the parameters of the biomass pyrogasification process used by the company. What is the problem of this process? That is a very green process. The problem is that these systems still produces some carbon-based ashes, about 1 kilo per hour. So what is our idea? Our idea is to find is to try to analyze if it's possible to recycle these ashes, carbon-based ashes, and to verify that this kind of ashes can be added to the same epoxy resin that I talked before, in order to have an effect not only on the mechanical properties of the epoxy cured resin, but also as catalyst for the same curing reaction. So it is very important for us to understand that we can have the same effect that we had with a nanofiller that was EGO, that was produced by University of Salerno, by using an ashes, some ashes, carbon-based ashes that are at the moment waste, that are waste for this company. So at the moment, the potential uses of carbon-based ashes, similar to the same ashes that we want to use in our project, mostly include the soil amendment and fertilization methods, followed by the production of construction materials and solvents, and the synthesis and production, for example, of ceramics and other materials. So the possibility to add these fillers, these waste fillers as catalysts for epoxy reaction is very innovative, original, and this is the first time that someone tried to reuse a waste material in this way. So the carbon-based ashes that were produced by the plant of the company could be considered an economic and environmental burden for the company. So for this reason, the goal of our project is to propose innovative solutions for the recycle of carbon-based ashes, with consequence increase of the efficiency of the company waste management and the reduction of its negative effects on the environmental and also on all the population. So I told you that not recycled carbon-based ashes are used as a catalyst for oxidation application. But we wanted to try, because based on the promising results that I presented before in the first part of my work, we decided to try to evaluate if the recycled carbon-based ashes could be used as possible catalyst for the cross-linking reaction of epoxy resin. I want to tell you that we prepared two different types of filler from the carbon-based ashes produced by the company. And you can see that we wanted to produce a first kind of filler that we call it, I show you, that we call it DBA. So for obtaining the DBA filler that you can see in this slide, we milled the ashes for 24 hours by using an horizontal oscillatory mill operating at 25 Hz. On the other hand, for preparing the ODBA ashes fillers, we oxidated the milled particles using hydrogen peroxide in a thermoset bath at 60 degrees Celsius and keeping the solution under magnetic steering for 24 hours, as you can see in the image of this slide. Afterwards, we added water and washed the whole mixture by centrifugation. Finally, we dried the fillers overnight on a hot plate at the same temperature. So here you can see also all the characterization that we decided to perform on our ashes before using them inside the same epoxy resin. So we decided to perform a very full characterization by structure, dimensional, morphological point of view. So for example, also chemical point of view. So we performed XRD, TGA, FTIR, SEAM, but also ADX, and so on. So a lot of characterization were performed to characterize the fillers before adding them inside the epoxy matrix. Then we decided to use DBA and the ODBA fillers inside the same epoxy resin that I told you before. And in particular, we use also the same curing agent, so isoforondiamine from the same company. And for preparing the epoxy ashes composite, we added an amount of DBA and ODBA filler equal to 3% by weight in order to compare our results with that we obtained in presence of the nanometric EGO filler. So the filled epoxy mixture were stirred for 5 hours, as you can see in the schematic representation that I reported in this slide, at 80 degrees. And then 22 pgr of isophorodiamina was added to the filled resin mixtures. We cured the samples at 60 degrees Celsius for 1 hour at and then at 150 degrees for 2 hours. So we performed the same study. So the aim of the project was to analyze the curing reaction of the filled and unfilled epoxy resin in presence or in absence of the carbon ashes fillers by using the same experimental techniques that we used before, and at the same time by using the same kinetic models that we used to predict the kinetic mechanism of the same systems in presence of the different kind of filler. So here you can see all the techniques that we experimental techniques that we used. So, and you can see also flexural tests, because in order to verify that this kind of filler can also act as a loading filler, able to increase the mechanical properties of the cured systems, we also wanted to perform some mechanical properties of the filled and unfilled cured resins. So let me know very quickly to the kinetic results that we obtained by using the experimental DSC that I showed you before. And you can see in this slide that we studied the curing reaction of the epoxy systems in presence and then in absence of in presence and in absence of the filler. And we also decided to study the kinetic mechanism of these systems by using a very well-known autocatalytical model that is Cool-Kenny model. So this figure shows a comparison between the experimental proof and the kinetic prediction. As you can see, we obtained a very good comparison between the experimental results and the theoretical prediction. In this slide, I also want to show you the results that we obtained when we characterized the fillers, the carbon fillers by FTIR or by SEM, because it's important to know that before using these particles, that they are carbon-based particles, and we also wanted to know the shape of the particles and, for example, all the information about the dimensions of the particles. I have not time to show in detail all the results that we reached, but if you are interested, all these results are also reported in a paper that I can share with you. So let me know very quickly to the part that now we wanted to stress in this presentation. It has we want to analyze, I remember, I want to stress again that the aim now is to understand if these waste ashes are also able to act as a catalyst for the curing reaction of the same epoxy resin. So we studied the cure reaction by isothermal rheological test, as you can see in the figure on the left, and we evaluated the evolution of the storage modulus and the loss modulus of the unfilled and filled epoxy mixtures as a function of time. So we also determined in this case the gel time as the cross point between both the modulus, so G the first, G second. And as reported in the table of this slide, you can see that the gel time of the net resin remained approximately constant when we added the DBA filler. So in this case, we don't have an effect of this kind of filler on the catalytical as a catalyst, but it is significantly reduced in presence of ODBA filler, as you can see in the last part of this table. So this data suggests that a catalytical effect of the oxided filler on the epoxy cross-linking is obtained. So we also studied the curing reaction of the filled and unfilled epoxy resin by dynamic DSC scans. So we used the area under the exothermal curves to calculate the heat of reaction for each sample, as you can also see in the table in this slide. Next to the principal exothermic peak and 130, the spectrum of the net resin, so the black curve in the graph, presents a shoulder located at about 145 Celsius degrees, and it will be due to the esterification reaction. Similarly to the epoxy DBA composites, displays a higher exothermic peak located at the same temperature and a shoulder at about the same temperature. So the intensity of the exothermic peak increased with the presence of ODBA filler, according to the results that we obtained by rheological measurements. So we also performed isothermal DSC scans on the liquid mixture, as reported in the next slide, in particular in the graph on the left. So we considered the reaction complete when the heat flow curve reached a constant value, and we used the area under the exothermal curve to calculate the heat of reaction at the test temperature. So as you can see in the table, the peak time reported in presence of the oxidized filler, so ODBA filler, decreases strongly. You can see in the last part of the table has already observed for the gel time. So this result further confirms the catalytic activity of the oxidized ashes towards the epoxy amine reaction. So we obtained a very important result between the catalytic effect of the oxidized ashes is also more evident in DSC, in particular in this kind of DSC isothermal measurement, rather than in dynamic scans that I showed you before. And this is probably due to a reduction of the ODBA effect upon heating above 50 degrees Celsius, which decreases its efficiencies as a catalyst. In fact, in the dynamic scans, most of the heat of reaction is developed when the sample is above 19 Celsius degree, probably when the chemical composition of the ashes is changed. So it's very important to notice that it's we need to use these ashes before this temperature if we want that they act as catalyst for the reaction. On the other hand, the catalyst has no significant effect on the heat of reaction of epoxy resin, as you can see from the table that is in the previous slide. And these results indicate that the carbon ashes doesn't significantly affect the maximum degree of reaction, but only the curing time. So you can notice the difference between the waste ashes and the nanofiller produced in the laboratories of Professor Guerra. So for each mixture, we also wanted to calculate the isothermal rate of reaction, and we represented it in the graph on the right as a function of time. So the table also reports the rate reaction peak and model parameters of the net epoxy and the composite resins obtained by interpolating the isothermal rates of the reaction data with an autocatalytic model of Cool and Kenny. You note that M is associated with increase of the reaction rate at the beginning of the reaction, so you know, I told you before, low values of alpha and before the peak, while N prevails in the final part of the reaction, you also know that high values of alpha are related to N. So the lower value of N observed when the oxidized filler ODBA is used indicates that the autocatalytical effect is higher than that of the net epoxy resin. So let me go to the final part of the work, when we wanted to study also the effect of these waste fillers on the mechanical properties of the cured systems. As you can see in this slide, the flexural modulus of the composite systems increases by about 50% when we add just 3% by way of DBA and ODBA fillers. You can also see that similarly the strength and strain to break improve in presence of the fillers. In this case, you don't notice a difference between the two kinds of filler that act in the same way on improving the mechanical properties of the net epoxy resin. So the result obtained in this part of the study confirmed that the oxided ashes fillers acts also as catalysts, reducing the cross-linking occurring time of thermoset matrix, but both the filler can act as a loading filler, able to increase the mechanical properties of our system. So it's very important results. So the epoxy resin, you know, is the most widely used resin for a lot of industrial applications, such as, for example, paints, coatings, adhesives, and also structural application. So these results is similar to that we obtained by using different kind of fillers, carbon-based fillers, such as, for example, the oxided graphene oxide that I showed you before, but also in presence of carbon black oxided filler. In addition, of being a very low-cost recycled material, the carbon-based waste filler, unlike the other carbon-based fillers previously used, shows a double important role, reinforcing and catalyzing the cross-linking reaction of the resin with amines. However, the ashes required a mechanical treatment and an eco-friendly oxidation procedure to perform the function of catalyst in the epoxy composites. So, in conclusion, we propose the double important role of the carbon ashes as a reinforcing filler and catalyst for cross-linking reaction of the epoxy resin with amines, and an innovative role as a filler, for example, in different kind of applications, able to improve the mechanical properties of the curing of the cured systems. So the work needs to be continued, I know. And I want to thank, before concluding my presentation, all the authors of our joint papers and also all the people that collaborating with me in order to perform the experimental and theoretical characterization of these systems. In particular, Professor Maffezzoli of the University of Salento, Professor Guerra of the University of Salerno, Professor Eleonora Ferrari of University of Leuven, and Dr. Domenico Cirillo of CMD company, and also the PhD student Enrica Stasi that is working with me and with Domenico Cirillo and Eleonora Ferraris on the project related to the ashes, and finally a postdoc student that is working also in our team, that is Antonella Giuri, and Maria Rosaria Acocella that worked with Professor Gaetano Guerra at the University of Salerno. Thank you to all of you for your attention.
Thank you very much, Professor Coccione, for your nice and interesting presentation. I start sharing my screen. I want to remember to all the attendees that if there are any question for the first talk, they can use the pop-up in Zoom. And now I will directly go to the second speaker, Professor Viktor Remeyev, that he is over 20 years old work experience. He is assistant professor, associate professor, and full professor division of computer science, elasticity and mathematical modeling of Department of Mechanics and Mathematics of Rostov State University, South Federal University, head of the Laboratory of Smart Material in Southern Scientific Center of Russian Academy of Science. He is a researcher of Martin Luther University, Halle-Wittenberg, and Otto von Guericke University, Magdeburg, Germany. He is professor at Rzeszów University of Technology in Poland, and he is a technical authority in applied mathematics and mechanics of solid, and his experience includes education, teaching, and programming. So, Victor, please share your screen, and the talk have the title Anti-Plane Surface Waves in Media with Surface Structure and Surface Interfaces, Discrete and Continuum Models. Please, Professor Remeyev, share your screen, and you can start with your presentation. Thank you very much.
Okay, thank you, Francesco, for the nice introduction. Very detailed, really. I'm really appreciated. So from this, it's clear that I spent a lot of time in different places, in different institutions, and probably it's not the last place, but okay. So first of all, I would like to thank organizers of this meeting. First of all, Professor Tarnabeni, who invited me using our common friends to participate in such kind of webinar, which is a new experience for me in sense of such kind of virtual conferences, which starts this year. And also MDPI organizers from the MDPI side, which sent just in time some reminders how to do links, etc. So I thank to these ladies, both ladies who participated here, and also other staff from MDPI who organized recently a series of very nice journals like Nanomaterials, Nanomaterials, Symmetry. So it would be very nice to publish in such a journal, which is, let's say, very good from many point of view. So now I switch to my scientific part. And to be honest, in this scientific part, it will be less experiments, let's say no experiments, and more mathematics. So in some sense, this presentation is complementary, the nice presentation of the previous lecturer. It is very nice to hear some kind of carbon structures and some kind of lattices which we see here. We saw during this presentation. Here, the main aim of my lecture is to consider anti-plane surface waves. In so-called media with surface structures and surface interfaces, and the main aim was to consider both discrete and continuum models. This work was done in collaboration with some people, and some part related to discrete was done with Basant Lal Sharma from the Indian Institute of Technology, Kanpur, India, and my colleague and friends from Paris Est, Solana Eli and Giuseppe Rossi. Of course, some other people were involved, so I also would like to thank Mohammad Malikan, who bring my attention to this kind of webinar, and probably we will continue to present next, if it will be continued, some more related papers to this. Okay, so there is outline of my lecture, and to be short, it looks like that. We considered two models related to so-called surface elasticity. This is a most useful model called Gerten-Murdoch model of the surface elasticity, proposed in 70s. So, and we considered a specific case of surface waves called antiplane surface waves here. And from both point of view, surface elasticity, it means we consider continuum approach and lattice dynamics. Then the basic, and probably from my point of view, the most interesting result will relate to this so-called scaling law, which brings some correspondence between lattice dynamics and surface elasticity, and some kind of example of surface interface, and some future steps. Okay, the aim of the lecture is to discuss similarity and difference in surface waves propagation in elastic half space, considering two models, surface elasticity and lattice dynamics. Roughly speaking, we have two problems, which is shown in sketch here. We consider it half space with surface stresses and lattice. For simplicity, we consider it a square lattice where we have some particles, or let's say for simplicity atoms, which are different in the bulk and on the surface. Why are we interested in such a problem? Nowadays it's known that some materials at nanoscales exhibit completely different properties from ones in the bulk. So the typical explanation of such differences based on some kind of models which introduced so-called size effects. We should mention here such models like strain gradient elasticity, stress gradient elasticity, and other non-local models. Also some kind of lattice approaches based on discrete approaches with local and non-local interactions. And last but not the least is the so-called surface elasticity. So surface elasticity is a quite simple model, simple in some, let's say, approximation, which based on such kind of generalization of classical surface tension. When we consider fluids, we know that there is a surface tension which is responsible for the shape of fluid drops and could be important, very important at micro and nanoscale, because in this case it forms the shape of the elements like drops of fluids and even for solids. And for nanoparticles, it's known more than 100 years. For example, the melting temperature depends on size, and so on. From the mathematical point of view, such model like surface elasticity brings changes in boundary conditions. So we have to use the classical solutions in the bulk, in the volume, and apply non-classical boundary conditions. So within this model, we have a lot of publications, and Gerten-Murdoch model is one of the simplest here, because it describes something like that. We have the elastic material, elastic solid body, covered with some elastic membrane. And stresses in this elastic membrane are responsible for so-called surface stresses. Unlike fluids, they are not isotropic, so it could be sharing. They relates to in different way for stretching in different direction and so on. Okay, so left part of this picture express this material, and this thick line relates to surface tracings, where here we have some kind of how to say lattice, and here we have some atoms on the surface which are different from ones in the bulk. The difference consists here in the mass and also stiffness of bonds. We consider it a linear behavior, so we have bonds here, and this bonds is different at the surface and in the bulk. Okay, now I switch to mathematics. And before mathematics, we considered some few references. First of all, it's two papers related to surface elasticity. And for latest dynamics, I refer to classic books by Born Huang, Brilliant, who considered this, let's say, matter in much more details. For this surface elasticity, it was discovered that there are some kind of specific anti-plane surface waves. Let me note that in classic elasticity, such wave does not exist. But in media with surface elasticity, with surface stresses, such waves exist, and they are studied in some papers mentioned here, and how it looks like. Okay, let me remind Gerten-Murdoch model of surface elasticity. We consider the simple formulation, simple linear model of Gerten-Murdoch, which looks like that. We have displacement field here. We have constitutive equation in the bulk. We have the strain energy density in the bulk. We have stress tensor in the bulk. For simplicity, we consider it isotropic material with two Lamé moduli, elastic moduli, and we have kinetic energy. Kinetic energy introduced also mass volume density. We have rho is a typical density. So nothing else, we have the classical elasticity here. In addition, we independently introduce the surface energy. And surface energy looks like energy in the bulk, but with two new called Lamé surface elastic moduli, mu s and lambda s, surface stresses, and surface strains. So this epsilon is just nothing else as just stretching and sharing of a membrane. And what is crucial here, we also introduce the kinetic energy at the surface, which looks like that, and m is the surface mass density. So it could be easy to understand how it looks like. For example, if you imagine the glass plate with deposited metal film, then this metal film has a mass which brings us kinetic energy. For derivation of governing equation, we use the Lagrange approach. So we consider variational statement for least action principle. We have the Hamiltonian functional, and this Hamiltonian function consists of two parts in the bulk and parts on the surface. We make a machine who produce a motion equation and natural boundary conditions. And from this, we have some kind of interesting results. What is interesting in the case of antiplane surface waves? Antiplane deformation looks like that. So here we have the simplest deformations. We have only one scalar function depending on two variables, spatial derivatives, and it is this displacement directed in direction of the third direction. For this case, everything is significantly simplified, could be simplified. And for this displacement amplitude, we have such kind of representation for harmonic wave. A harmonic wave looks like that. We are looking solution in this form. You have some amplitude, an exponential part with all where we have the wave number and frequency. So if we substitute everything here in our equations, we obtain nothing else as wave equation here. And what is interesting, we have also a specific non-classical boundary condition. This boundary condition looks like equation 10. And from point of view, if I may say, from point of view material in the bulk, it plays a role of boundary conditions, but from the point of view of elastic membrane, this is its own motion equation, whereas this right part is just external action from the environment. Okay, we substitute everything, our solution, into this equation. We found this is a rather simple procedure. We found the form for amplitude for capital U. We have this representation of exponentially decaying solution with the depths. And we have the whole solution which looks like that. And substituting this solution into boundary conditions, we have so-called dispersion equation, which relates omega with k. So we have this solution. This solution could be solved analytically, what is very interesting and very, by the way, useful. So we have this solution in this form. Okay, this solution is similar to lab waves. It describes the behavior of such so-called lab waves and exists only under some conditions when shear wave velocity is lesser than shear wave velocity in the bulk. Okay, now let us consider square lattice. Now we switch to discrete world. So we have discrete coordinates. So we have integer numbers here. We have displacement are still continuous, but they are given only in discrete in the lattice points. So instead of partial differential equation, we have ordinary differential equation, which looks like finite difference equation. And here this notation means that this is a displacement given in these points with these coordinates. So for example, this element is given and in the point with coordinates x plus 1, y. So at free surface we have boundary conditions, but here in discrete world we have some kind of ordinary differential equation which is not symmetric anymore because we have bonds which are different, and alpha is the factor which differ the connections elastic, let's say roughly elastic springs make them different from the ones in the bulk. Okay, and capital M is also something which is factor related to mass of surface atoms, surface particles. Okay, then we can consider the discrete analog of the surface wave considered previously, and this discrete function looks like that. It's completely different. What's the technically different? We obtain the dispersion relations given by two equations. So it's some kind of implicit form for dispersion relations. Here we have psi and we have omega as usual, and this guy, this eta, is just a parameter for this case. Formally we can exclude it, but it brings very awkward formulas. So let us now we have two solutions. We have two dispersion relations formulated for continuum and for a discrete lattice. And now what is our main aim? We should find some similarity and some kind of correspondence between parameters for lattice and parameters for continuum. If we succeed, we can say that, okay, we can use some lattice, known lattice parameters to characterize the surface elasticity parameters, or vice versa. We can consider it experimental data from surface waves and surface elasticity to find the properties of elastic properties of the lattice. Okay, first we should quite natural. We introduce also mass. This is a mass of atoms, and we relate it to density, introducing the density as the mass of some elementary cell. And K also related to shear modulus like this with some factors. Then after that, we can reformulate our dispersion relation for the lattice in this form. And it's still based on discrete approach, because here we have only discrete numbers. If we try to represent it in the graphs, we can see the following. We have the dispersion relation, we have phase velocity c here, we have k wave number. What is the difference? Here we have region between cs and ct, we have the region when all of these waves exist. C0 is a dispersion relation related to unlimited, unbounded square matrix. Here we have classical, let's say, classical Gertin-Murdoch model, which is green line. Here is just for Gertin-Murdoch model. And here we have this discrete dispersion relation for lattice. Because we consider the first Brillouin zone, this curve is ended here, so we faced with the first difficulties. Considering discrete model, we cannot prolongate this red line up to infinity, because it exists only for discrete number of parameters. Nevertheless, we try to compare this green and these red lines somehow. For these dispersion relations, luckily we have some kind of formulas. For this, in between, we have the classical formulas for squared lattice, unbounded square lattice. And we used such kind of, as you see, all of dispersion relations started from the same point, which is because we already use something like first correspondence principle, which looks like here, which is absolutely consistent with our first assumption, which we made about this capital M, capital and small m, etc. But now we should do something else. This something else relates, let me switch to how these ends of these curves related. In other words, we try to approximate properly this dispersion relations. And for this, we have such kind of scaling law. 27 is the main result of this, let's say, lecture, which relates to the scaling law, which express that the most interesting here is that this parameter should size dependent, and should size dependent in such a way when the A is just, I remind you that A is just a cell size, lattice cell size, and when it goes to infinity, we have some kind of correspondence. Mu s must go to infinity in this case. So if we don't do such kind of assumption, like, don't make such assumptions, we considering some continuum limit. Continuum limit, it means when we consider it lattice size, cell size goes to 0, we can forget about any surface phenomena because it will be negligible. And to keep it, we should do something like some kind of upscaling to this. In this case, we have some relations between lattice parameters and wave velocities in Gertin-Murdoch model. And in fact, this is some kind of relation between continuum and discrete model. So having enhanced parameters for one model, we can calculate the parameters for another model, considering the dispersion relation. And here we can see some pictures when we consider finite but different lattices. Of course, it is just already dimensionless. Alpha now is A is now dimensionless. It looks like that. So we can approximate this green by red or vice versa. So for any finite number of wave parameters, we can approximate lattice or Gertin-Murdoch up to any accuracy. Of course, at the end, all the time we have some difference, which could give us another possibility for another scaling law related to we can approximate these and that points, try to make them close, but this makes price because in this case we cannot approximate this. So for short waves we have very good correspondence between two models if we assume these laws. And also such kind of correspondence was done between strain gradient model, which called Tupin-Mindlin model of linear strain gradient elasticity. It could be done also in this case. We also can some kind of correspondence between surface elasticity and Tupin-Mindlin model. And so it will have also such kind of situation when we can characterize some parameters of strain gradient elasticity using the surface elasticity. But this is just qualitatively because there is some kind of also differences between these models. And what is useful in this case, and what is useful, for example, both models which we considered are ideal in the sense there are no defects, no imperfections, nothing. We have plane, we have ideal lattice, we have ideal continuum, there is nothing else. Instead, if we consider some real materials with imperfections, it makes it difficult to find analytical solution or something looks like analytical solution for such a case. But for example, here, considering lattice dynamics, we can find such kind of solution for analytical solution for such surface interface. We have in the bulk everything the same, but on the surface we have two different coatings, let's say, with different atoms on the left, on the right. You can see, I hope you can see the difference between these balls here. And we also considered some surface wave propagations. And now this main question, what happens when we have such interface? This is just a change in properties and material properties on the surface. Nothing else. It could be model different coatings, some boundaries with coating, some defects, like micro cracks on the surface, etc., etc. And what happens here? It happens very interesting things. First, we introduce discrete model here. We have discrete model in the bulk. We have the classical square lattice here. We have surface layers on the left here and surface atoms on the right. They are different from the bulk and from each other. So we have kind of surface layers with different atoms. And for this, we can formulate equation of motion, and what is called now is boundary conditions. Here, what is interesting, equation of motion in the bulk are the same, but on the surface, for discrete model, we have the motion equation for one part, for the second part, and also we have the motion equation for interface. Because if we consider the atoms here, for example, his neighbors are different. He has one neighbor from the one kind of neighbor from right and another neighbor from the left. So we have a difference. So unlike continuum models, here we have additional ordinary differential equation describing the atoms lying exactly in the interface. Okay, so we have a set of ordinary differential equations given for different points, and we can try to solve it. And this solution was mostly done by my colleague from India, Basanlal Sharma, who is very good specialist in the field of lattice dynamics. And we considered incident surface wave and considered transmission, leaking, and reflection of such kind of waves. So we are looking solution in this form for incident wave. And finally, we got a solution for such approximation. We consider it not a half space, but we consider it a strip, just a strip of n, capital N number of layers. We have large number of layers, so we can consider n as, let's say, is large enough. It is just, of course, it's approximation, and from, let's say, from continuum point of view, the solution for a strip is more complicated than for lattice dynamics. Here is not the case. It could be done analytically. And finally, we have some fluxes here. So we have everything in one picture. You've got reflectance, transmitters, and liquid energy. So interesting that for my point of view from practical application, it's also interesting that such kind of interface may result in energy flux propagated into the bulk. And you see that we have the reflectance. You have some kind of reluctance here. Black thin curves gives reflectance. Transmittance, you have some transmittance, and not always it could be transmitted. And also we have some kind of frequencies. We have very good energy propagated into the bulk. So we considered here different number of atoms, up to 8 here. And here I should say something about the future step and possible applications. First of all, we considered surface interface for very specific particular class of surface waves. So this is just antiplane surface waves, which is reduced to wave equation. Is not like relay. It is interesting because they exist only in media with surface energy, whatever this means. And of course, it will be interesting consider another kind of models like more complex lattices, and what is more interesting, let's say diatomic lattices and more complex particle interactions. So there is a conclusion which I would not like to read because we have some comparison for these models. And what is interesting, we introduce some kind of scaling law related to relations between discrete and discrete lattice dynamics and Gertin-Murdoch model. What is interesting, such kind of scaling law is also given by another people considered some kind of interfaces or surface layers of finite thickness, so-called rigid or stiff interfaces or stiff interface or stiff skin, let's say, in the case of plates, in the case of wave propagation along some non-perfect interfaces. So this is just in the same region. So having different languages using discrete model, surface elasticity, we have the same results. There are some references related to these presented results given here. And thank you for your attention. Grazie, Emilia.
Thank you very much, Professor Remy, for your nice and interesting presentation.
Thank you so much.
And also for your Italian speaking.
My Italian speaking is not so, it's some kind of mystification. Okay. I can say that io non parlo italiano. Un po'.
Yes, it's all right. Now we have time for questions, and we can start directly. Wait a moment. So we have time for questions, and I have 2 questions for the first speakers and 2 questions for the second speaker. So I stop sharing. Professor Corcione, please. Which could be the industrial repercussions linked to the result of your research? Has the company considered the practical application? So if you want to share your screen to answer this question, you can. And please, thank you.
Okay, so thank you for your question. I think is a very important question because the results obtained in our work that I presented today, I think they are very important for the technological applications. Since the catalytical effect of the carbon-based nanofillers has a lot of advantages. And I didn't have the time to show you all the advantages that are related to this important innovation and properties of the ashes waste fillers. For example, among the advantages that I want to share with you, there is the fact that this innovative procedure is a one-step procedure that can reduce the curing time, and so we can have faster reaction. At the same time, we have milder processing conditions and also higher cross-linking density, and all these advantages that I now illustrated to you can have a lot of opportunity for the industrial applications in terms of reducing the time to produce the same material or improving the performance of the materials. And at the same time, they are reached by reusing waste materials that at the moment are just a problem for the company. And we tried to find a solution to use a material that is a waste for the company. So I think the advantages are very important.
Okay, thank you for your answer. So I have another question, and it is: are there any other possibility to recycle the ashes that may allow the use of a larger quantity?
Ah, yes, okay. So the goal of this project, as I told you during my presentation, is to propose an innovative solution for recycling the carbon-based ashes with the consequent increase of the efficiency of the company waste management and the reduction of its negative effects on the environment and also on all the population. However, we would like to analyze not only the possibility to recycle the carbon-based ashes for the close linking reaction of the epoxy in resin, but also, for example, as the recovery of the carbon-based ashes as fillers in conductive inks for bioelectronic application. This is a part of our project, in particular of the project in collaboration with the University of Leuven, where at the moment the PhD student is for her period abroad. And finally, for example, we also would like to reuse the carbon-based ashes as reinforcing fillers in thermoplastic matrix, for example, in the starch. To be used these starch films filled with the ashes, for example, for agricultural applications. For example, in this latter case, I think it will be possible to use a larger quantities of the ashes as you proposed me.
Okay, thank you very much for your answer.
Thank you.
Now I will skip directly to the second speaker, Professor. Yes, Professor, you have an answer, question?
I'm very sorry, I haven't question, but just maybe interesting comment to this agricultural application. I recently read interesting paper about Amazon rivers and this region.
Mm-hmm.
It was interesting that time, before the presence of these conquistadors from Portugal, from Spain, etc., there are Indians who produced so-called terra preta. It's artificial, let's say, ground for growing enormous production. And what was interesting, they use exactly carbon ashes, but they produced it from, let's say, from trees. They just fire trees. They may organize some garbage with these trees. And what was interesting, that the Portuguese even took these, let's say, ingredients to bring to eastern part to the country, to Brazil, just to use it. And I finally discovered this terra preta is used, let's say, in many countries which haven't, let's say, normal, let's say, ground for agriculture to improve. What was crucial that this porous carbon ash was used for use there. So it's very nice, let's say, from any point of view.
Okay, thank you very much for sharing. Yeah, for sharing with me this.
Thank you very much for the nice lecture.
Okay, thank you also for your suggestions. So
no, it's just a comment. I read it 2 days ago.
Yeah, thank you. Thank you.
Thank you too.
Now I have 2 questions for Professor Remeyer. And the first one is, as you consider square lattice only, what should we expect in a more general case?
This question is very nice, and thank you for this question. First of all, let me note that square lattice is quite simple, and for this square lattice we have exact solution. Exact, it means that we have analytic solution. Unfortunately, if we consider it another simple square, not simple lattice like triangle lattice, such kind of solution is not known. At least for me, for us, it's not known. Formally speaking, it should be the same behavior, but it is not proven. And square lattice has also interesting properties because it brings so-called cubic symmetry to the model, which is not important for this case because for such kind of anti-plane shear waves, it doesn't matter because it's not affected. But if we consider triangle or diatomic lattice, it should be the same results, but the technique, unfortunately, is more complicated.
Thank you very much for your answer. And I have another one. What do you think on surface wave propagation in the case of stress-driven local elasticity?
This is also a very nice question because we have what we have here. We have something which is called surface energy. This surface energy could come from the material difference in the surface because it's typical explanation which we got, at least I don't know what is going in physics in current schools, but in my time it was in school explanation of surface tension. We have a difference on the surface and difference in the bulk, so we have surface energy, and we have such kind of approach which is based on mathematics, and mathematical models looks like that. We have some kind of strain gradient elasticity. Roughly speaking, we have the energy depending on strains and gradients of strain, etc. We have just a surface elasticity which looks like we have additional concentrated energy concentrated on the surface. We have non-local elasticity of Erringen time, so-called stress-driven, and you should know, and for sure you know this better than me, when we have stress gradients, gradient of stresses, and we have mixed models. And I did such calculations for non-local for both models. And it is interesting that qualitatively we have similar behavior for these models for surface elasticity. But for example, this dispersion curve for Gertin-Nordek elasticity is bounded by curves from Tupin-Mindlin and from Erringen type of elasticity. So they both models give some kind of bounds for this. So this is quite interesting question and also related to some non-localities, because we have different kind of non-localities here, which should be described in different manner. And this non-locality could bring similar behavior, but qualitatively different. Qualitatively, it should be different.
Okay, thank you very much for your answers.
Thank you for your questions.
So I think that I control. We have no other questions. So I want to thank you very much for the Professor Merayev and Professor Colcioni to be here and to share your interesting topics to our community. And want to thanks to NDPI companies to give us the possibility to share with all of you our research topic. And so now we can conclude. I want to thank you very much for all the attendees to be here and to have the patience to hear our research topic and interest research topic. So thank you very much to all of you.
Thank you very much. Thank you, Francesca.
Thank you.
Thank you, Carola.
Thank you. Have a nice day.
Charlotte, yes, have a nice day.
Thank you very much and have a nice day.
Yes, Karen, if you want to conclude this webinar, you can. So if you want to say some things and for the conclusion, you can. And So, Karen?
Thank you very much for your time and for your efforts, and have a nice weekend and all stay safe.
Okay. Thank you
Okay.
very much. Bye bye. Have a nice weekend.
Bye.
Ok, buona
Bye, good
serata,
morning.
buona serata.